Hello guys, in this video we will discuss about Gauss-Jordan method. This method is used to solve a system of linear equation. In our previous video we discussed Gaussian elimination method, which is also used for the solution of the system of linear equation. So first I want to discuss the difference between these methods, because to some extent they looks like same, but actually they are not. In Gaussian elimination method, we reduce the augmented matrix to row echelon form. But in Gauss-Jordan method, we reduce the augmented matrix to canonical form or the row reduced echelon form of the augmented matrix. So this is the major difference. In Gaussian elimination, we reduce the augmented matrix to row echelon form, while in Gauss-Jordan method, we will reduce the augmented matrix to reduced row echelon form. So basically, you should know what are these two forms of the matrices, to which you can see this video in which I explained what is row reduced echelon form or what is a row echelon form of a matrix. So let us begin the Gauss-Jordan method. So we will solve this example with the help of Gauss-Jordan method. We have the system of linear equation as x plus y plus 2z is 9, 2x plus 4y minus 3z is 1, 3x plus 6y minus 5z is equal to 0. So first we will write down the augmented matrix of the given system of linear equation. So you know that augmented matrix of the system of linear equation, just write down the coefficient of x in one column, coefficient of y in second column, coefficient of z in another column or the third column, and the right hand side entries as the fourth column. So if you have more variables, then the number of columns will be increased according to the system of linear equations. So the augmented matrix is given by this matrix. So first step is we have to reduce this augmented matrix into reduced row echelon form. So first let us make this term as 0. So how we will do it? We will use the row operations to do so. So in place of row 2, multiply row 1 by minus 2 and add in row 2. So that you will have minus plus 2, it will be 0. Similarly, in row third, to make this entry as 0, so you will do the row operations as multiply row 1 by minus 3 and add in row third. So you will get in the second equation, you are multiplying row 1 by minus 2, minus 2, minus 2, minus 4, minus 18, and you have to add in row 2, 2, 4, minus 3, 1, add them, it will be 0, 2, minus 7, minus 17. So you have 0, 2, minus 7, minus 17. Now in the row third, multiply row 1 by minus 3. So you will have entries you are multiplying by minus 3. So minus 3, minus 3, minus 6, minus 27. Add in row third, 3, 6, minus 5, 0. Add them, 0, 3, minus 11, minus 27. So you will have entries as 0, 3, minus 11, minus 27. Now we have to make this term as 0. So for making this term 0, so we will do the row operations in row third. Multiply row 2 by minus 3 and multiply row third by 2. So what we will have, row 2 by minus 3, 0, minus 6, 21, 51. Row third by 2, 0, 6, minus 22, minus 54. Add them, 0 minus 6 plus 6, 0. This is minus 1 and this is minus 3. So we have the matrix as entries 0, 0, minus 1, minus 3. Two rows, first two rows will remain same, 1, 1, 2, 9. First non-zero entry must be 1. This is the condition for the reduced row echelon form. So we will first non-zero entry in the second row, it is 2, and here we have minus 1. So in row 2 divided by 2, and in row third multiply by minus 1. So we will have 1, 1, 2, 9, 0, 1, minus 7 by 2, minus 17 by 2, 0, 0, 1, 3, because we multiply by minus 1. Now, the other condition for the reduced row echelon form is that these are our leading entries or the pivot elements. So another condition for the reduced row echelon form of a matrix is that in that particular column, that pivot elements are the only non-zero entries. It means we have to make this term as 0, we have to make this term as 0, we have to make this term as 0. So let's do those operations so that we can make them as zeros. As we have to make this term as 0, so we multiply row third by 7 by 2 and we will add in row second. It means we will do this row operation. In place of row 2, multiply row third by 7 by 2 and add in row 2. Also, we have to make this term as 0. So in row third, multiply by minus 2 and add in row 1. So it means in row 1, we are doing this operation. In place of row 2, that means in row third multiply by 7 by 2. So we will have 0, 0, 7 by 2, 21 by 2. Adding in row 2, 0, 1, minus 7 by 2, minus 17 by 2. Add them, you will get 0, 1, 0, and this is. So in row 2, we will have 0, 1, 0, 2. Now in row 1 we have to do this operation. Row 1 as it is, 1, 1, 2, 9. In row third multiply by minus 2, 0, 0, minus 2, minus 6. Add them. So 1, 1, 0, 9 minus 6 is 3. So in row 1 we will have 1, 1, 0, 3. Now we have to make this term 0. So we will do this row operation in row 1. Just you can take this row operation r1 minus r2. So we will have 1 minus 0 as 1, 1 minus 1 is 0, 0 minus 0 is 0, 3 minus 2 is 1, 0, 1, 0, 2, 0, 0, 1, 3. So now if you see to this augmented matrix, this is in reduced row echelon form or in canonical form. Why? Because each leading entry is 1 and it is the only non-zero entry in their corresponding columns. So that means this augmented matrix is in reduced row echelon form. So now we will write down the corresponding system of linear equation to this matrix. It will be this system of linear equation, and when you solve it you will get the value of x as 1, y is equal to 2, and z is equal to 3. So this is the solution of the system of linear equation by Gauss-Jordan method. So let me summarize this video. What we have done initially, we have a system of linear equation which we have to solve by Gauss-Jordan method. So we write down its augmented matrix. We reduce this augmented matrix to reduced row echelon form, and then from that augmented matrix we write down the corresponding system of linear equation, and at this step instantly you got the values of unknowns. That means the desired values of the variables, and this is our Gauss-Jordan method. That's it. If you like this video, please share it and subscribe to my channel. Thank you so much.